Good afternoon, everyone. We'll wait just a minute to allow everyone to join the seminar, and then we'll begin. Good afternoon, everyone, and welcome to the University of San Francisco's MSDS seminar series in data science. My name is Sean Butcher, and I'm the Partnership Director for the Data Institute. This seminar series is brought to you by the University of San Francisco's Masters in Data Science program and sponsored by USF's Data Institute. Each year, we partner with companies and organizations around the San Francisco Bay Area and beyond to provide 9-month seminars, internships for our students. During their degree, our master students spend 15 hours a week working with the company to tackle their data science and analytics problems. If you or your organization is interested in supporting the Data Institute or working with one of our students, please contact us by email at datainstitute@usfca.edu. Alternatively, you can visit us on the web at www.usfca.edu/data-institute. As a reminder for students interested in joining our next cohort, we are still allowing applications for our MSDS program, so please get those applications in as soon as you can. Today, I'm pleased to welcome Ben Nachman, who Ben is a staff scientist at Berkeley Labs, and today he'll be speaking with us about machine learning and how it is being used in fundamental physics research. We will leave time at the end of the talk, and Ben will answer questions during the talk, but please enter your questions using the Q&A button at the bottom of the screen. We won't be answering questions if you enter them in the chat section, so please use the Q&A button. Welcome, Ben.
Hello, thank you very much for the invitation. So I'll now switch over. All right, you can see my slides, I hope. Shall I begin?
Yep, I can see your slides, yes.
Yep. Great, very good. Okay, thanks so much. Today I'll tell you about machine learning for fundamental physics, and today I will start by telling you a little bit about the science and motivate why it is that we're interested in these kind of questions. So first, what is fundamental physics? I want to understand and probe the fundamental structure of nature, and I promise I won't spend too much time talking about the science, but I have to at least say a few things. So there are deep theoretical and experimental questions that motivate this exploration. For instance, you may have heard of the Higgs boson, which was the last fundamental particle discovered. It won the Nobel Prize a few years ago. So that's, in discovering it, it opened a whole new set of questions, which we want to understand in more detail. There are other interesting questions as well. For instance, if you ever looked up the picture of a neutron online, you'll see that neutrons are made of quarks, and it looks kind of like, see pictures that look like this with down quarks and an up quark, but in reality, actually looks more like the right picture, and we don't understand why that is. There are also other interesting features of nature that we've uncovered that we don't understand their origin. So for instance, there's dark matter. Most of the universe is made of matter. We don't understand what it is. And it's been discovered astrophysically, but we haven't been able to produce it in a lab yet. And there are other interesting properties of subatomic particles called neutrinos, which have a non-zero, but really, really tiny mass. We don't totally understand why. So all these questions together have motivated us to probe the fundamental structure of nature in more detail. And we've performed thousands of hypothesis tests to try to uncover new structure. And so far, we've found no significant evidence for new physics beyond our current theory of everything, which is called the standard model. And so this really has motivated us to develop new tools to explore our data in new ways. Okay, so in order to do that, we've built a lot of detectors. and to cover various types of fundamental physics experiments at different length scales, different properties. So astrophysically, or in the lab, or in other environments. And I just flash a few experiments here, but I want to throw some numbers up so that you can get a sense for why fundamental physics and these giant detectors are really starting to are solidly in the big data regime. So let me focus on one example. So this is a picture of the ATLAS experiment at the Large Hadron Collider. The Large Hadron Collider is a 30-kilometer proton-proton collider in Geneva, Switzerland, and it's currently the highest energy, most powerful accelerator in the world. You can see if you stare, these are the people. So to get a scale, so the actual detector is like it's 5 stories, 100 meters below ground, and a single collision that's recorded by all the various components of the detector result in something like megabyte per collision, and the collisions happen at 40 megahertz. So that's 10 terabytes per second, and we run for all year for many years. And so this is something like zettabytes per year. I had to look up what 10 to the 9 or 10 to the 8 terabytes is in the units. Is it's starting to get into this crazy amount of data. Now in practice, we actually throw away a lot of the data in real time and with some online processing. And so the actual data that we save at the end of when it's all said and done will be sort of in the exabyte scale. And just to give you a sense, so Google is like tens of exabytes. And so this is not the biggest data set that's ever been made ever, but it's sort of in the regime where it's way bigger than many other scientific data sets and many other industrial data sets as well. Okay, now a brief aside about these experiments. So for instance, this experiment I just told you about, it's huge, not only in the size of the detector, but also the number of people who work on it. So I'm part of this experiment, the ATLAS experiment. There are about 3,000 people who work on it. And here's just a small fraction. This is actually 10% of the collaboration. We were we were celebrating the discovery of the Higgs boson some years ago. Just to give you a sense, the big data we need many people working together from all over the world. And another interesting feature of having so many collaborators is that whenever we write a scientific paper, our papers include all of our collaborators. And so I have 3,000 collaborators, our papers have 3,000 people. So the author list of our papers usually takes up more pages than the paper itself. And so here I just took like a screenshot of what the author list looks like. We don't fight over the ordering, it's all alphabetical. So we have a collaborator who's has a very fortuitous last name. So he's always listed first. And if you scroll through all the pages, you eventually find my name, and then you can scroll to the bottom and find Berkeley Lab. It's one of the collaborating institutes. Okay, that was an aside, but now back to the topic. So that was detectors. In order to push the frontier of fundamental physics, we don't need more than just new detectors. We also need new methodologies, and so we have really extensive simulation program that's based on a variety of first principles and phenomenological approaches that are very computationally intensive. These simulations and methodologies many times will be run on supercomputers. We have a supercomputer at Berkeley Lab where a lot of our simulations are run for particle collisions, detector interactions, astrophysical phenomenon. Additionally, we have other methods that are improving the state of the art. So for instance, accelerator technology in order to make synthetic particles in the lab, and other methodologies as well. But all this together, I like to think about this as sort of I call it the hyper challenge. It's a challenge and an opportunity in the sense that we're trying to probe a very high dimensional space. And we're trying to do that with detectors that are very complicated. And they have many, many channels for redundant measurements. And so you can think of them as like hyperspectral cameras. So we have this high dimensional space we're trying to probe with a high dimensional detecting technology. And putting those together makes for a big challenge. And just to give put some numbers behind that. So a typical collision at the Large Hadron Collider, for instance, might produce thousands of particles. Each of those particles has momentum. So that's 3 numbers, px, py, pz, and then might have other numbers as well, like electric charge. And so that's a 1,000-dimensional space that we'd like to be able to measure. And we make that measurement with a series of detector elements that are represented here with these colors. So imagine we collide protons, out goes a bunch of particles, they interact with our detector, and then we measure them with a series of redundant readout channels. And for instance, in the Atlas detector, there's something like 100 million readout channels. So you can think of it as 100 million pixel camera. In reality, it's more like a series of photos that are sort of built from redundant layers that allow us to infer something about the particles. But this is an extreme challenge. So we're combining this hyperspectral camera with this high-dimensional hypervariate space that we're trying to probe, and that's the underlying challenge which will motivate the use of deep learning. And so, in particular, we've been conducting multivariate analysis of collision events for a long time using shallow learning. However, recent advances have opened up a new way of looking at our data, and I like to think of deep learning as sort of a hypervariate vision to probe our data and its natural high dimensionality. And perhaps one of the reasons that we haven't found any surprising signs of new structure yet that will help explain some of the mysteries that I talked about in the beginning of the talk is because we're simply not looking at the world in the right way. And if we put on our hypervariate vision goggles, we would be able to expose new structure. Okay, so this picture is my take on what the analysis workflow is in particle physics, and it's very similar in a lot of related areas of fundamental physics. And so in particular, it's sort of two parallel workflows. So the right-hand side is sort of like the experimental workflow. So we want ultimately to learn something about nature. In order to do that, we build experiments, big experiments. And from these experiments, we have a large set of observables that are measured in our detectors. And then we want to make sense of the large number of observables, so we do some pattern recognition. And the pattern recognition allows us to cluster various detector signatures together to reconstruct the trajectories of particles, then to group particles together into meta objects. And then from those, we can then make sense of the collision debris. The parallel track is the theory side of things. And so we want to construct a theory of everything, which in principle should describe nature. And so we take this theory of everything, which has a relatively small number of parameters, and we can use that theory to calculate and simulate what would happen in an actual experiment. And so we have very comprehensive simulators that allow us then to produce basically the same output that we would observe in our experiments. So we have the same high-dimensional detector level observables. We can run the same pattern recognition as we do with actual data. And then we can compare the high-level features, in data and in simulation, and then that allows us to basically run inference. So we can compare, we can use the left-hand side to infer something about nature on the right-hand side. So that's the general setup, and this is something actually, in fact, that I think distinguishes our setup a bit from other areas of science and industry, in particular because we have these excellent simulators and we can run the left-hand side all the way from beginning to the end. So given some parameters, we can really simulate everything as if it were real data, and that allows us to run a very precise inference. Okay, so now that machine learning is coming into the game, it's playing a critical role in basically all areas of this workflow. So on the right-hand side, machine learning is being used for online processing and quality control, for the actual detector running and data taking. And then for the pattern recognition, it's playing a key role in data curation. So in particular for clustering or various other aspects like calibration, particle identification. There's a wide variety of tasks here that are being accomplished now and improved with machine learning. And also on the theory side of things, machine learning is also playing a key role. So in particular, going from the theory of everything through physics simulators to detector level observables, this is being improved with various machine learning methods that allow us to speed up or supplement existing simulators. And I'll say more about that in a little bit. But we can also run the reverse arrow. So I said we ultimately want to do inference. Inference means look at the data and infer something about the underlying parameters. And we can also use machine learning to help us with that, basically to go from the detector signatures back to our theory of everything. Okay. So for the most widely used place machine learning is the most widely used application of machine learning in particle physics is for sure this red arrow here. So the dimensionality reduction to do pattern recognition. And so I'll say a little bit more about this, giving some specific examples. Okay, so there's a lot of tasks that are involved in dimensionality reduction. So you can imagine we have some low-level signatures that are read out in our detector. And you can imagine at the lowest level, there's literally the electronic readouts in our detector. They produce some signals, and we have to figure out what to do with them. So at that level already, pattern recognition already plays a key role. But then there's mitigating noise and sort of running some kind of clustering to group nearby correlated signatures. Then we have to calibrate our detectors because they're inherently biased. We can remove the bias. And then we can tailor the final observables to a particular analysis to increase the sensitivity for some objective. And I'll give some examples for some of these in the next slides. Okay, so for instance, let me give you one example, a concrete example from noise mitigation, where machine learning can play a role for particle physics. So here's a picture of a proton-proton collision at the Large Hadron Collider. The purple lines here correspond to charged particle trajectory. So in the main picture, the protons are sort of coming in diagonally, and then out goes all the collision debris. And the inset in the bottom left, it shows basically along the beam direction, zooming in just in really, really close to the collision point. And the reason I show this picture is because at the LHC, we don't just collide single protons at a time. That would be very wasteful. Instead, we collide many, many protons at a time, but only one of those we care about. So in this inset here, the teal lines correspond to the trajectories of charged particles from collisions that the one collision that we care about. And you can see they all sort of, can be projected back to a single point in space. So that's like that was the location of the proton-proton collision that we cared about. And all these other collisions, the ones that are in purple, and you can't really see very well, but there are these little red dots that correspond to the other vertices. Those are other extraneous proton-proton collisions that are a source of noise. And so this is sort of like image denoising. We have all these detector signatures, some of which correspond to an event we care about, and the rest are particles we don't care about. And so we want to be able to remove the contribution from these pileup collisions, which just add soft radiation on top of all of our events. And there are a variety of different techniques that can be used to do this, but in particular, there are tools for image processing that can be used. So imagine I think of our detector as sort of like a camera. And so if we have a proton-proton collision, out goes the collision debris, we could project the energies that are measured onto the surface of a cylinder. And then this cylinder basically can be viewed as like a grayscale image, where the pixel intensity is something like the energy deposited in that particular location in space. And something that's sort of different about these pictures compared to, say, a normal grayscale image is that I mentioned that this sort of hyperspectral in the sense that it's not just a single, we don't have one layer, we actually have multiple ways of detecting particles. And in particular, we can tell if the energy comes from charged particles or neutral particles. And so we could actually form not a grayscale image, but like a colored image. So an RGB kind of image where you can imagine like the red corresponds to the charged particles and like the green corresponds to the neutral particles. And there's one more twist which is that for the charged particles, we can tell if they come from the collision we care about, whereas for the neutral particles, we cannot. So there's sort of 4 different sets of particles. There's the charged particles from the collision we care about, the neutral particles from the collision we care about, the charged particles from the collisions we don't care about, and the neutral particles from the collisions we don't care about. And the point is that we can use 3 of those images to predict the last one. So we only get to measure the sum of the energies from the neutral collisions. And so we have the charged image from the collision we care about, the charged image from the collisions we don't care about, and then the total neutral. And we can use those 3 to predict the neutral from the collision we care about. And so that's what's kind of shown schematically here. We have these 3 images. Each one is a grayscale image. They're shown here in color, but they're just single. The z-axis here is just the pixel intensity. And then we could input those 3 images to, say, a convolutional neural network, which is a standard tool in image processing, to output a prediction event by event for the neutral image for the collision that we care about. So it's a strange sort of noise where we get to measure something about the noise event by event, and then we can use that to predict what is the noise-free image. Oh, I see there's a question. So the question is, how do you determine the location of the specific proton-proton collision you care about? Yeah, so we can determine it by reconstructing these vertices. So we get to measure all of these trajectories. These, for instance, in the teal here, these are all reconstructed trajectories of the charged particles, and then we can cluster them in space to determine this location where they all intersect, and we can determine that very precisely. And then same for all the other collisions we don't care about. For the charged particles, we get to measure their trajectories. For the neutral particles, we don't get to measure trajectories. That's why you can't tell where they come from. Only for the charged particles. All right. So now let me go back to the pipeline. So once again, here's the picture I showed about different levels of the application of machine learning in the data analysis chain. And now let me give another example. So I just talked about noise mitigation, but now let me talk about an example from tailored analysis observables for particular physics analysis using kind of similar techniques. So here's another picture of a proton-proton collision. The protons now come from the left and from the right, and they collide in the center of the detector, and then out goes the collision debris. The orange particles, the orange lines correspond to charged particle trajectories, and the green and yellow blobs correspond to energy deposits in a series of calorimeters. So a calorimeter just measures the amount of energy deposited in a local position in space. And one of our goals is to identify new massive particles. So when the protons collide, sometimes, if we're lucky, they might produce the famous question mark particle. And we want to see if we can identify the decay products of the question mark particle. And if you remember E equals mc squared, in order to make more massive particles, we need to pump in more energy. We can basically trade energy for mass. Okay, and the most effective way of doing this would be to use all of the information from the collision debris in order to do the inference on what produced the collision. Okay, so this is the same picture as before. I've just cropped it. And as I mentioned earlier, we can imagine projecting the collision debris onto the surface of the cylinder. And if we do that, then we can make images of the event. And so thinking of the whole event as an image, we can have, once again, sort of RGB kind of image where we have, say, the charge, the neutral, and other channels as well. And so those look like this is like one of the one particular image. So the pixel intensity is the energy deposited in a particular region of the detector. And one thing you notice right away is that these images look nothing like natural images. They're very sparse, and there's some just basically looks like blobs. So it's very hard to tell by eye what happened because there's no clear structure. Only on a statistical basis can you tell. And we can combine information globally across the whole event with sort of local information. And so you could imagine that there are some regions of the detector, like this region that has a little bit of a hotspot, we could sort of zoom into that region and say, this region is a particular interesting one. Let's focus on that one with high granularity. And so one possibility is to combine sort of local information with regions of interest. And as before, you could imagine processing these images with a convolutional neural network, which is, yeah, sort of state-of-the-art image processing. There are a couple of interesting challenges. So in particular, this is a cylinder. So if you have this periodicity in the angle, and so if you apply normal convolution, then the neural network has to learn that there's something strange happening at 0 and pi, or 0 and 2 pi rather. And so one way you can get around that is actually implementing what we call a padding layer. You literally just copy everything on the left, at 0 to 2 pi, and then it helps the network learn that actually 0 and 2 pi are the same. But in any case, you could construct kind of a neural network architecture that has convolutional layers, and then they can be combined in order to answer the question, is this event from something new or is it from something standard? And if you do this, you can significantly improve the signal to noise ratio for particular physics targets. So here's a plot that shows the amount of data is on the x-axis and the signal to noise ratio is on the y-axis. So you want this to be as high as possible. And this is for the projected sensitivity for high energy Higgs bosons. We haven't observed high energy Higgs boson. We know the Higgs boson exists, but we haven't observed them at very high energy yet. And so the gray dashed line is sort of the standard classical approach to looking for these high energy Higgs bosons. And so it will eventually produce a significant result. However, if we apply this sort of machine learning technique, we can very quickly surpass the performance of the classical approach, and it will allow us to, using the same data set, discover this process much earlier. And this is sort of a reoccurring theme that happens all throughout particle physics, where machine learning has a significant potential to enhance sensitivity of existing tools. All right. So that was my series of examples for pattern recognition. But now I want to spend the next part of my talk discussing how we can use machine learning in other ways, which are maybe not just for standard classification tasks. And so then where I'm going to give first example is on this arrow here, where we can use machine learning to augment or supplement current simulations. And in particular, this goes under the moniker of generative models. Okay, and one of the reasons that this is an important task is because training a neural network can be slow, but evaluating a neural network can be extremely fast. So once you've trained a neural network, there's a big upfront cost, but then the inference is very fast. On the other hand, physics-based simulations of particle interactions are incredibly slow. They're very accurate, very precise, but very slow. And so, for instance, here's a picture of, so we shoot a particle at a slab of, in this case, it's a slab of liquid argon. And we can use complicated detector simulations to model how those particles interact with the material and deposit energy. And so that here's like a three layers of liquid argon, and the colors correspond to the amount of energy deposited in that part of the detector, and the widths here just correspond to the physical width of the argon. And so the question is, can we take the best of both worlds? Can we use a neural network that has a large upfront cost but is very fast to evaluate, to combine with a physics-based simulation to basically make a fast simulation approximation? And that's where generative models come in. In case you're not familiar with generative models, they're just like other kinds of classification or regression models. A generator is nothing other than a function, like any other regression model. But here it maps noise to structure. So basically, you have a function like the green arrow, and you feed it a series of random numbers, and out comes structure. That's like what a generator is. And we would like to generate, say, images that correspond to the energy pattern that we would see inside our detector. And one tool to do that is the Generative Adversarial Network, or GAN, which is a very popular tool these days. And it solves the problem of making a generator in a very elegant way by basically having two neural networks that compete against each other. So there's one neural network called the generator that maps noise to structure. That's what we ultimately, that's the only thing we actually care about. And then we learn a second neural network called the discriminator that tries to distinguish, it looks at sets of images and tries to distinguish images from the generator from images from our physics-based simulator. And if that second neural network cannot tell the difference between the generated images and the real physics-based images, then our generator has done a very good job and is generating photorealistic images that should match the physics-based simulator. All right, and one can apply this in practice, and it works pretty well. So this top row shows the average images for particles of a given energy that we've simulated hitting this three-layer calorimeter. So there's the first layer, the second layer, and the third layer. The two coordinates correspond to like the two angles in the transverse direction. And the bottom row shows the same average images, but now from the neural network. And qualitatively, they agree pretty well. There are clearly some artifacts, and some of those artifacts can be fixed with modern tools, modern tricks. But you can also examine quantitatively, which I'm not going to show you all the plots, but basically it works pretty well for reproducing even the fine details of the distribution of energy inside the different components. One of the main reasons that this is exciting is about the speed. As I said, that was the main reason that motivates the study in the first place. So in particular, the physics-based simulator, which is called GEON, so it takes this amount of time for to generate a single image. Whereas if you train after you've trained the generative model, you can then evaluate it, and it's much faster. So if you evaluate it on a GPU, which is graphical processing unit, it can be 10 to the 5 times faster than the physics-based simulator. And so clearly these numbers can both change as the technology improves, but I think this is really quite an exciting tool that can be used to really quantitatively and qualitatively change the game when it comes to doing inference with our simulators. Okay, now back to my roadmap. So I just talked about the direction from theory through to simulator, but we also, of course, want to do inference. That is to go from the pattern recognition back to a theory of everything. And so one challenge is that simulators are great. Simulators can very precisely map our parameters to the data space, but they're typically not invertible. So they're a stochastic model. We have some parameters and we can generate events from them. But for inference, we want to go on the reverse direction. We want to look at the events in our detector, and we want to be able to infer the parameters of the model. And so that's not possible with a simulator. Okay, so just to highlight this inference challenge, we get to observe in our detector various detector signatures. So blobs of energy in our calorimeters and reconstructed charged particle trajectories. But we want to infer the actual particle properties. So where were the particles? What were their types? What was their energies? Those kind of questions. And one way we could do this is if the standard way would be maximum likelihood. So if I knew the probability density of the measured spectra given the true spectra, given a true spectrum, I could then just say, okay, well my best guess for the particle level distribution is simply the one that maximizes the likelihood of seeing what I saw. And that would be great. However, as I had mentioned earlier in the talk, the point is that we have a hyperspectral camera. So the red here is some really high dimensional space, and the true that we're trying to infer is also high dimensional space, so also very complicated. And so probably of measured given true is intractable. It just basically can never write down that density. And so we can't maximize it directly. However, we have the simulator, so we can sample from P of measured given true very effectively. That's what a simulator does. It goes in the forward direction, but not the backwards direction. And so there are a variety of tools that have been developed recently that go by the name of simulation-based or likelihood-free inference. So the idea is that can we develop tools where we do maximum likelihood approaches without ever having to write down the likelihood itself? And because we rely so heavily on simulations that are often not differentiable, this is an area where I think particle physics may be making significant contributions to machine learning in general. Okay, so let me just give you one example of how this could work, which is based on the fact that it may be very hard to write down the likelihood in order to maximize it, but sometimes it's very easy to write down the likelihood ratio. So imagine I have two probability densities. So I have sample 1 and sample 2. Sample 1 is from P, sample 2 is from Q. If I learn a classifier to distinguish a sample drawn from P and a sample drawn from Q, it turns out you can interpret the likelihood, you can interpret the classifier output as a likelihood ratio. And so you can basically train a neural network, for instance, and that to distinguish the two data sets. And if you interpret the output as a likelihood ratio, you can directly learn Q over P. So that's great. It turns the problem of density estimation, so learning Q and P separately, into the problem of classification, which is much, much easier. And then there are some tricks for how you use the likelihood ratio itself to actually maximize the likelihood. But you could imagine that if I had this ratio and I have a reference, then I could use the reference, say it's P is the reference and Q can change. I can use a series of classification tasks to then basically find the Q that maximizes the likelihood. All right, so this is particularly useful for particle physics because our data have a complex structure. So in particular, you might have, every event has a different number of particles. The collision debris is very complicated. So you have, many, many different particles, a different number of them every time. And also there's no natural order. So basically it's a variable length set. That's what our data look like. And here's like a picture where you can imagine this colliding particles, out goes some debris, and every time you collide, you get a different debris. And so this is hard to do with generative modeling, but it's much easier to do with the classifier. And I'll just flash one plot to show that basically it works. So here's a case where, at least in simulation, we have a variable length high dimensional space that we would like to run this inference task on. And I can't visualize a variable length high dimensional space, but we can project the space into a small number of one-dimensional observables. So for instance, this is like the histogram of the number of particles. And this is a histogram of some other observable that's more complicated. And the point is that we start with some prior, and then we can do this likelihood ratio trick to do maximum likelihood to achieve the target. So the blue is where we started with. The black is sort of like the data, so we'd like to learn. And the orange is the maximum likelihood estimate that we've achieved by using this classifier trick. And so this is fantastic. So we've been able to do maximum likelihood in a multi-dimensional, multi and variable dimensional space. All right. Okay, so now back to my roadmap. So that was about inference. So I told you about using deep learning to go from the theory of everything to the data space, and then how you can use deep learning to also go backwards, to go from the data space to the theory of everything to do inference. And in the last part of my talk, I want to tell you about how we can use deep learning to actually do anomaly detection. So to look for strange patterns in data, in some cases even without using models. So basically just on the right-hand side without the left-hand side. Okay, so here's the picture again about colliding protons looking for new particles. the current search program at the, for instance, the Large Hadron Collider, it's built on positing a particular theory of everything. For instance, supersymmetry, which is a particular theory that might be true. And then given that theory, we can construct an analysis strategy that uses a simple combination of observables in order to see if that theory is true or not. But the question that I want to know if we can solve with deep learning is, can we relax the model assumptions to explore high-dimensional feature spaces? So not using simple combinations that are model dependent. So really going from some model-specific case to the real question mark case. Right. So the question is, what if we're not looking in the right place for the new phenomenon, which is exactly the question I started off the talk with. So part of the problem is that we can't just tell on an event-by-event basis what happened. So if you look at these pictures, the left-hand picture is obviously a cat, the right-hand picture is obviously a dog. But even if I could pay physicists to look at every event, all of the the many petabytes of events, it wouldn't be that useful, because it turns out even a well-trained physicist can't tell a particular collision event what was the underlying process. And that's thanks to quantum mechanics in part, because it's just not possible to know what actually happened on an event-by-event basis. It's only possible to know statistically. And so the kinds of anomalies that we're looking for are not ones in which you can tell from a single example if it was anomalous or not. And so this is a challenge for training. So usually if you're training a classifier, you say like, oh, I have a bunch of labeled examples where I have some that are, for instance, like the background process, and some that are the signal process, and I can train a classifier to distinguish, the red balls from the green balls. But what if I don't have label information? What if I have two samples of events that are mixed? They have a sort of a composition, some non-trivial composition of red and green, and I still want a classifier that distinguishes red from green, but I don't have per instance labels. And the question is, can I still learn? And the answer is yes. There are a variety of tools that fall under a class of methods called weak supervision. And one of those tools is called classification without labels. And the idea is extremely simple. You simply assign labels. So let's say this was your case. You have mixed sample 1, mixed sample 2. You could just call everything in mixed sample 1 a 0, everything in mixed sample 2 a 1. And then you could train your favorite classifier, neural network or not, to distinguish mixed sample 1 from mixed sample 2. And then actually you can show that classifier will be asymptotically optimal for distinguishing the green from the red, even though I didn't tell it that there were green and red and that individual instances were green or red. It just knows that there are two mixed samples. And so this is a sort of powerful methodology that you can use directly on data in order to try to identify anomalous kinds of events. And yeah, so one question, can we use this koala classification without labels approach to look for new particles? And yeah, just to be clear, this koala is being freed, not captured. Okay, so let's in this last part of my talk, I'm going to show you how you could use this classification without labels technique in order to look for new particles. So let's imagine that we have a situation kind of like this, where we have one particular direction in our feature space where we know the background is smooth, has no non-trivial features, and if the signal exists, it would be localized. We don't have to know where it's localized, but it has to be localized somewhere. And I use the letter M here because often this feature is a mass. And that's because if you have a new particle with a new particle that is some new massive particle, even if you don't know what the mass is, the reconstructed mass will be localized at the mass of the particle. So it's a naturally localized observable, whereas for the background, there's no reason for it to be localized. And then ultimately, we're going to scan over this dimension. And so in order to apply the classification without labels protocol, we need to construct two mixed samples. And we do that by making a signal region and a sideband region where the signal region basically should be localized on where the signal would be if there was a signal, and the sideband region will be close by. And the point is that the signal region, both regions are mostly background because we're looking for rare signals, but this signal region here might have a little bit of signal in it. And then what we can do is we can use other features that are available to us to train a koala classifier to try to distinguish the events in here, the signal region, from events in the sideband region, in order to see if there's any difference. And if the classifier can pick out a difference, then that will give us evidence that there's some subpopulation of events in this middle region, which is somehow different than the neighboring region. And those would be, that would be evidence for an anomaly. So now I'm going to just walk through an explicit example. It's a very important search at the Large Hadron Collider called the two-jet search. So this left picture is a cross-section of the Atlas detector where the protons are being collided into and out of the page, and the collision debris goes in all directions. And you can once again see these lines correspond to charged particle trajectories, and the yellow blobs correspond to deposits in our calorimeters. And these collimated sprays of particles are called jets. And this event sort of looks like there's some new massive particle, it decays into other massive particles, and those particles decay into other particles. And so you can imagine in the center of the detector, there's some new particle, and then these other particles decay into a spray of particles, which is why you have all this complicated structure. So the invariant mass of the system is the resonant feature. And then you can use all the other properties of the event to train your koala classifier. So let's see how this works in practice. So imagine I have simulated proton-proton collisions. This is the mass of the pair of jets. It's basically a histogram. So each point here corresponds to a different bin. And we can construct a signal region and a sideband region. And we want to be very precise here. So we can estimate how similar the signal region is to the sideband region by making a parametric fit to the data points, excluding the signal region, and then interpolating into the signal region and comparing the prediction to the data points. So you see the red dash to the blue points. And that will allow us to compute a p-value. And we want to know if the p-value is going to be really small. That will be evidence for something new. We can then train a koala classifier and repeat this procedure many times. So like the 10% line here corresponds to training a koala classifier and keeping the 10% most signal region-like events. And the 1% is the same, but it's the 1% most signal region-like events. And then for each one, we can do the fit and then interpolate and compute p-values. This will be our ledger of p-values. So p-value here is the probability of the data, the blue, given the background prediction, which is the red dashed line. And then as I advertise, we're going to scan from left to right. So we can scan the signal region from left to right. As I do, the 100% line doesn't change, but the other lines change because the classifiers learn directly on the data, and the data changes and move from left to right. So you can see as I go, the p-values are consistent with boring. They're all sort of relatively high, so there's no evidence for some anomalous events. Okay. So now that's good. If there's nothing there, it doesn't find anything. But that's obviously only, that's necessary, but not sufficient. So now let's inject a signal into the data stream and see if it can find it. So here's a signal that we've injected. It has some structure like this that has some particles that go by, have names at the end of the alphabet. And this signal is injected at a very low, there's a very low SNR. So you can see the background is here, 10 to the 5, and the signal is down here 10 to the 2. So without any machine learning, this signal is not findable. So now the question is, will the machine learning be able to automatically identify the presence of this signal? Okay, so let's do the same procedure. We can scan our signal region from left to right. And when the signal region is to the left of the signal, basically there's nothing interesting once again. But then when the signal region aligns with the signal peak, you could even just see by eye basically that the classifier is more efficient on the signal than it is on the background. And so the bump starts to appear by eye. In the limit where the classifier has learned, or the classifier is incredibly good, you'll have basically only signal and almost no background, and then you'll have a very prominent peak. And so now if you compute a p-value, you can see, I mean, you don't need to compute the p-value, it's going to be really small, but on the right-hand plot, we compute it. And basically go back. So here, the p-value here is something like 10 to the minus 12, which corresponds to a 7 sigma excess. So we've taken, a 1.5 sigma excess and transformed it into a 7 sigma excess automatically without ever telling the neural network that there's anything there. And then, once again, the p-values return to being, large when the signal is outside of the signal region. Okay, so yeah, just to summarize, when there's no signal, it doesn't find anything. And when there is a signal, it's able to automatically enhance the presence of the signal. All right. Okay, so here's now just an overview of the things I've talked about today. I've covered quite a lot of ground, discussing how machine learning is used for data curation, building, doing pattern recognition and denoising with detector level observables, how we can use machine learning for fast simulation, for doing inference, and for anomaly detection to automatically identify the presence of new structures in data. And that brings me to the end. So really, I've covered a wide set of topics today, although it's still, there's a lot more that I didn't get a chance to talk about. Deep learning has a great potential to enhance, accelerate, and empower discoveries in particle physics. We have some unique challenges, and those unique challenges will require dedicated solutions. With these new tools, we'll be able to fully exploit the data in their natural high dimensionality, enhancing the potential for discovery to answer some of those key questions I brought up at the beginning of the talk. All right, thank you.
Well, thank you, Ben. Let's give everyone a couple of minutes to see if we have any questions. And then we'll let you go. If you have any questions, please type them in the Q&A section using the Q&A box at the bottom of your screen.
So it looks like there's a question. What are my thoughts on string theory? I'm not exactly sure what you're asking. Maybe you could clarify.
I do have a question.
Sure.
You said a lot of the data you collect, you don't store. So how are you determining what to throw away and what is useful? Is it based on timings of collisions, or what is the, what type of criteria are you using?
Yeah, that's a really excellent question. So this is where a lot of model dependence is baked into the decisions. So we basically don't have enough disk space, and the latency is not good enough to store every collision. So we have to have some way of throwing out things. And some of it is heuristic. So we like things that are very low energy, we throw them out. Because there have been previous experiments that maybe likely would have seen things if they were low enough energy. But in a lot of other cases, we have some general ideas of the kind of things that would be interesting to look at, but there are some model dependencies that are baked in there. So for instance, Higgs boson events are saved with a very high efficiency. We know what Higgs boson events look like. We've designed the trigger system to save them very effectively. But there are other kinds of things that are look nothing like Higgs bosons that are probably not saved very effectively. So for a large part of the physics program that we've laid out, we save very, very efficiently. We save the data, but there are a lot of other things that we throw out, and a lot of the stuff we throw out people think is probably garbage. Garbage in the sense that it's like low energy things and probably things that doesn't have anything new. But there could be interesting discoveries in the garbage, and I think that this is going forward. It's probably we need to make sure that we're not really biasing ourselves, blinding ourselves from the new interesting physics by throwing away all those events in real time.
Do you mean, there's a lot of the energy in this this field has gone into building larger and larger and more expensive colliders. Do you see any benefits that machine learning might bring that would bring down the cost or allow us to use existing facilities to garner more information than we might have otherwise been able to gather?
Yeah, I think that machine learning will definitely increase the utility of existing experiments. It will help us design better, more effective experiments in the future. Unfortunately, the biggest cost drivers are things that are not really much you can do with.
Right.
To first order for a collider like the Large Hadron Collider, the cost is 50% the tunnel and 50% the magnets.
Right.
And yeah, it's true we're building better magnets, and going forward that will be really great. But a lot of that is hard to deal with. Yeah.
Okay, we have one question. Do you ever address the hyperdimensionality as a Newman theory, for example?
Yeah, could you clarify maybe what you mean?
Yeah, that seems quite specific. Okay, well, I think we're just about out of time. So I want to thank you, Ben, for your talk. And thank you for joining us and providing a lot of interesting information about how machine learning is being used. And I want to thank everyone for joining us this afternoon. I want to thank you all for your attendance, and I look forward to seeing you at future seminars. Thank you so much.